So it's a pleasure to speak here and to give this mini course. I will speak about representations of groups in the Lie group SL2 of C, so the 2x2 matrices with complex coefficients and invertible matrices. So most of the topic will cover the case where these representations have a dense image. I don't know if you remember the talk by Ilyashenko, where he explained some rigidity results about these kind of representations. But most of the topic will not be dynamical. It will be more algebraic. And so I will try to explain, to make an introduction about what I want to say. And so I will begin by writing the objects I will consider during these 3 lectures. So we take the Lie group SL2C, and in this Lie group, we take a finitely generated subgroup that will be denoted by G. And in most of the time, this group will be marked, namely, the finite set of generators will be specified. Okay, so this is a group with a finite set of generators. And so this is a marked finitely generated group. Okay. Then we will be interested in the following set. So the homomorphisms from G to SL2C, and sometimes, in fact, we will consider the representations in PSL2C, namely the quotient of SL2C by multiplication by plus or minus the identity, which is a little bit more richer because sometimes you have some groups which can be embedded in PSL2C but not in SL2C. But this is, you can just forget about this. So here sometimes also we will consider this set. And because the group G is marked, how do you define a representation of the group G in PSL2C? You just have to specify what is the image of the generators of the group, okay? And you will have to check that all the relations satisfied by the generators of G in G are also satisfied by the new matrices that you consider. So another way to say that is that this set can be naturally embedded in the product of R copies of PSL2C, where R is a number of generators. And this set is a certain subset which consists of a certain number of equations in the matrices you are considering. And these equations are polynomials. Thus, this set is a complex algebraic manifold. Okay. So this. So now. we will be concerned by the following problem. In fact, there are many groups G which can, algebraic structures of groups that can appear as a subgroup of PSL2C. And we will see some examples in the course of these lectures. But what we will try to do is, maybe a terminology that, so we will call special an irreducible component of, so that, for simplicity, I will denote it by lambda of G, of a manifold of the type lambda of G. And what happens is that if we make kind of drawing, so here let's consider PSL2C to the power R. Then there are some regions in PSL2C that will be referred to as regions of algebraic stability, where consisting, let's say, of matrices that generates a free group. And so let's, for instance, suppose that this region is the one I am, je suis en train d'assurer, I don't know in English how to say that. And then you will have the special submanifolds of this variety, which are sub-complex submanifolds, like that. Maybe you will have some points which corresponds to rigid representations. And in fact, what we will try to explain is that the special subvarieties are going to fill the exterior of the region of algebraic stability, and we will try to prove some that some of these subvarieties are going to be equidistributed in some sense in these regions. That could.
Could you say that I did not understand the 5 last minutes?
Okay, so what I say is that you consider PSL2C to the power R, which is corresponds to the special subvariety of the free group on R generators. And in that, you have a region of algebraic stability, which consists in the R tuples of matrices, which generates a free group.
So your picture is suggesting it's open?
It is not open.
So in the interior of the set?
Sorry?
Is the interior of the set?
No. Now I will not. I don't want to say what is the structure of the set. It can be complicated. I don't want to say it is open nor closed. It is not open nor closed. You have to add some hypotheses to have this kind of properties, but still, then you have, you're right. You're right, Etienne, thank you. You take the interior of that region of algebraic stability. So you have the set of R tuple of matrices which generate a free group. You take the interior of that region. Let's say that it is a region of algebraic stability. Anyway, by a region of stability, by definition, it is open.
This is not the space of discrete and free subgroups.
We will see that it is. We will see that it is. So then the complement is a closed subset. And in that closed subset, you see all the special subvarieties corresponding to other groups which are not real. And
countably many?
yes, there are countably many irreducible components. I mean, there are countably many special subvarieties.
When you say that there was algebraic manifold, this means that they are always finitely generated, not finitely presented?
The groups, yes, right.
Is always finite?
Yes, that's right. This is due to the Hilbert-Basis theorem, which says that indeed, if you have an infinite number of relations, then you can, because they are polynomials, you can, they are equivalent to a finite number of relations. So I come back here. So here you have these special subvarieties in the exterior of the region of algebraic stability. And what we will see is that first, the closure of the union of this special subvariety is dense. Okay, so this is well known. It was well known for a long time, but it is. And also, we will see that you have some equidistribution phenomenon for some special class of subvarieties, of special subvarieties. Okay, for instance, what we will prove is that if you take in the free group, you take a word on the generators of large length at random, and you say that this word is going to be the identity. Or more precisely, in fact, we will not be able to prove that, but we will take the square of the word. You take a word that's random and you take the square of the word, you declare it is identity. So this is an abstract group, and it can be embedded into PSL2C. And we will prove that the special subvariety that it defines is going to be more and more dense in this region of algebraic instability, and is going to equidistribute with respect to some currents or measure, for those that do not know what it is.
How do you say that if you choose a group at random, it will embed in PSL2C?
No, this is because I just take one relation, and it is the square, because you can if the trace of the words is the trace of the rotation of angle pi, okay, which is going to happen sometimes because the trace is a polynomial function, hence it's going to take this value, then you get a group like this, generically. So this is really because we have just taken one. If we take too many, probably it will not be true. So just I would tell you, so of course, why do we restrict to that group? So I choose that group because first, the techniques that I will use are going to be techniques of complex analysis, and so I need a complex Lie group. And for the phenomenon that we want to explain, we need that the group is enough rich, namely we need that it is not solvable. And this group is the first non-solvable complex Lie group. So I took that group, but many of the results I will explain generalize. Not all, but many of them. But I wanted to be as elementary as possible. So we will stay in this setting. Now, also, I would like to explain why in the title of this mini course there were dense representations. In fact, we will mainly be concerned with representations with dense image. Because apart if the group G is a free group or a surface group, the special subvariety corresponding to G is going to consist, I will not, it is not a result, but just philosophy will consist of dense representations. So general, if you do not consider free groups or surface groups, and there are many others. For instance, I will give you an example. So suppose that G, so in PSL2C, it is a really rich group which contains a lot of discrete ones, namely and even co-compact or of finite covolumes. These groups corresponds to hyperbolic three manifolds. So consider G, so let's say a finite covolume subgroup, discrete, a discrete with k cusps. So this means that if you consider the quotients of the hyperbolic three space, which whose groups of isometry corresponds to PSL2C, then you find a hyperbolic three manifold which is not compact, but it has some cusps, homomorphic to the product of a torus by a semi-real line, and the core is compact. So then we can consider, so this is a subgroup of PSL2C already. Yes?
So what is the core? Compact core and finite covolume, or is it possible?
So what I wanted to say what I mean by K cusps. And in fact, I am a little bit not precise here in the sense that I use some results, but I want to say that K cusps corresponds to the fact that if you consider the quotient of H3 by the group G, then this is a complete hyperbolic manifold which has a compact core and K cusps homomorphic to the product of a torus by the positive real numbers.
It's not what is usually called the complex core.
No. Yes, let's say a compact. Here you have a compact part. I don't know. Yes, maybe. And okay.
It's called usually a thick part.
Thick part. Okay. So what is interesting here is that if K is equal to 0, we know that this group is rigid by Mostow rigidity theorem. Okay? Namely, the connected component of G in lambda G is a point. Okay? But if K is positive, then lambda G, I mean the connected component, so I denote by lambda G not the connected component of lambda G which contains G. Then this certain proved that this contains a K-parameter family of distinct or non-conjugated representations of G in PSL2C. Of non-conjugated representations. And in fact, one can prove that a generic element in this K-parameter family is dense. So in this special subvariety, you will have just one discrete representation, and almost all the other ones are going to be with dense image. So that is the reason why I wanted to say that.
What means dense image?
I mean, the representation is a map from G to PSL to C, which is a morphism. So the image of this map is dense in PSL to C. Yes, so let's say, I will, so a terminology, a representation. From G to PSL to C is dense if the closure of rho of G is equal to PSL to C. Okay. So today I will not prove this equidistribution results that I announced. Actually, this result is a result that we proved with Romain Dujardin. And I think I will explain this result in the second lecture, or third lecture. And I hope that in the third lecture, I will have time to for a gift to Javier. But we will see if time permits. So, okay, so the first, so let us denote by dr of G the set of dense representations. So, as a subset of the set of homomorphisms from G to PSL to C. Okay? So the first theorem I would like to prove is that this is an open set.
G is that group, or what group is G?
G is any group. G is any subgroup. So G is any subgroup of PSL to C. So the proof of that theorem consists in two parts. So what we want to do is the following. You take a representation which is dense. And you want to prove that if you perturb, so this representation is given by just the image of the generators. And you want to prove that if you perturb the image of the generators as matrices, then it will still be dense. So there is two steps. Step one, by perturbation, the representation is non-discrete. And the second step is that indeed it is dense. Okay, so let's explain the ideas to prove the first step. So the step one is can be proved by looking at the dynamics of commutator mappings close to the identity. So it is clear by calculus, differential calculus, that if A and B are matrices close enough, let's say, distance 1 of the identity. So this is identity matrix. Then, if you take the commutator of A and B, which we usually denote it by this notation, and you look at the distance of this commutator to the identity, then it's going to be a constant time, at most a constant times the product of the distances of A and B respectively to the identity. So it is a differential calculus. You just compute the second derivative of that map here, and you see that. So suppose that A and B are close enough to the identity so that this holds. Okay. Now we will define a sequence like this. So A0 is equal to A. A1 is the commutator. So let's say it's going to be a sequence. So it will be better. It will be nicer to do that. So B1 is the commutator of A and B, etc. Bn plus 1 is the commutator of A and Bn. So namely, you take B as the first term, and then you take the commutator with A, and the commutator with A again, etc. You iterate the commutator with A. And because of this relation, if A is close enough to the identity, then, in fact, Bn is going to converge exponentially to the if are close enough to E. So, to prove that a group is non-discrete, we have to prove that there exists a sequence of elements of the groups which tends to the identity but is never the identity. So here we have a good method to prove that, to produce sequences that converge to the identity. But then we need a criterion that will say that in fact these matrices are not the identity for every n. That I will let as an exercise. This criterion, I read it in a paper by Loret and Rebello. It is a simple criterion that they just use in LMR. Suppose, so we take A and B, which are close enough to the identity. Now, suppose that B is diagonalizable. But it's different from the identity. It has two different eigenvalues. And that A and B does not commute. So namely, the first term of the matrices is not the identity. Bn is different of the identity for every n. Okay, so this is an exercise that I let you do. It's not really, so you have to prove that if for some n, Bn is the identity, then in fact Bn minus 1 is also the identity by, and you will get by decreasing induction that in a contradiction. So now it is clear that from this, it is clear that if you take a representation with dense image, you will be able, because these two conditions are open conditions. If you take a diagonalizable matrix with distinct eigenvalues, then in a closed neighborhood of this, it's going to still be the case. And if two matrices does not commute, it's also will be true by little perturbations. So we can find in the image of our representation two matrices which verify these conditions. And these conditions will still be verified by small perturbations. So by applying this, so by defining the sequence for these perturbations, we will find in our perturbed representation a sequence of matrices contained in the image which converge to the identity and which are not the identity. So the image of this perturbation will not be discrete. So we have proved the step one. So now I will prove the step two. And the step two, we will use Lie theory. So we will look at the adjunct action of PSL2C on its Lie algebra, which is defined by this formula. If you have a matrix A in PSL2C and a matrix M in its Lie algebra, which is the set of 2 by 2 matrix with a trace is equal to 0, then the adjunct action acts by conjugation by A. And this is a fact that I will not prove, that this adjunct action of SL2C in its Lie algebra is irreducible, in the sense that there is no, and even irreducible on R. Namely that there is no vector space, real vector space, which is invariant by this action. So there does not exist a real vector space invariant by add. So this real vector space would lie in the Lie algebra. So of course, unless it is 0 or the whole Lie algebra. And I will not enter into the, I will not do it, but you can prove that if the adjunct action of PSL2R on its Lie algebra is irreducible, then if you look at the action of G on the Lie algebra, which acts by the adjoint. So I will write it. So I claim that if you consider the action of G on the Lie algebra of PSL2C, because it has dense image, okay, this will also be irreducible. Because if there would be an invariant vector subspace, real invariant vector subspace by this one, it would also be invariant by the closure of the image of that representation, which is all the image of the adjunctation of PSL2C on its Lie algebra. And in fact, so here it is not so evident, so this is clear. But what is not so evident is that if is a small perturbation of O, then this will still be true. Why? Because to be irreducible means that there is no fixed point of the adjunctation when you act on the Grassmannians. Okay, on the different Grassmannians corresponding to the real subspaces of the Lie algebra. And having no fixed point is invariant by small perturbations because the Grassmannians are compact spaces.
Are you using there that the representation is not discrete when you say that the first statement with the transaction?
No, here I don't. So
When you say that
so here I use because of course I use that because rho is dense. And here I don't use anything. Okay? So now how we conclude? So if you look, so you take a small perturbation rho prime which verifies that. So you look at rho prime of G, and we want to prove that this is dense in PSL2 of C, so we look at the closure of that. This is a closed subgroup, so this is a Lie group. Okay, and we have to prove that this Lie group is indeed the whole of SL2C, and for that it is just sufficient to prove that its Lie algebra, it's the whole Lie algebra of SL2C. Then by connectedness of PSL2C, we have what we want. But this is a subspace invariant by this representation. So sorry. So if you take the tangent space at the identity matrix of this is a vector subspace contained in the Lie algebra of SL2C, which is invariant by these representations, and because it is irreducible, it is either 0 or the whole Lie algebra, but it cannot be 0 because we have proved that the representation is not discrete, so that this group has positive dimension. Okay, so this ends the proof of that theorem.
Theorem which is the opposite. Usually discrete representations are open.
Sorry, discrete representation are what?
Open.
Discrete?
Yeah.
What do you mean by open? Ah, in the spatial variety. Yes.
My wife, what is the full generality for that?
No.
You have the theorem that the space of discrete or dense representations is open.
No. Okay, so here. Okay, theorem that I will not prove, which goes in the opposite direction. the set of faithful discrete representation is closed. Okay? This is a theorem by, I am not sure I am right, but I think it is a theorem by Shukrov. So you have a closed set. So let's say, for instance, so here I will draw some really simplifying picture. So here is a faithful discrete. So here we are in a lambda of G. And the exterior of that, most of the points are dense representation. But it can appear that there are some isolated points or something like a curve of representations, which are, for instance, non-faithful but discrete image. Okay? But by perturbation, when you will perturb that, you will see that some elements were mapped by the identity and then no more mapped to the identity, so they become non-discrete and, in fact, most probably dense. Okay, it is more clear. But if you get out the set of so I think that maybe I am wrong. But I think that these are the only, or you can have a representation here, which by chance or malchance is going to be non-discrete but not dense. Like, for instance, with value in SL2R. So you will have here some manifold consisting of representation whose image are dense in SL2R, for instance. I don't know if it answers the question.
I don't know.
Okay.
If you take the group G, it's just C with one generator.
Okay.
So this theorem,
okay, so I am okay. So all right. Yes, maybe I have forgotten a non-elementary hypothesis. Yes. Okay. So yes, that's right. Of faithful. So what does mean non-elementary? That means that. Okay. So let's. So we will do this a lot. Namely, we will consider the action of PSL2C on the Riemann sphere. So I recall that PSL2C acts on the Riemann sphere by Möbius maps, and the automorphism group of the Riemann surface P1, CP1, is exactly PSL2C. And definition, a non-elementary representation is a representation which does not preserve any probability measure when it acts on P1. It's not really English, I think, but does not preserve any probability measure. Right. Yes, yes, you could have, right. Yes, sometimes even people don't speak about limit set if it is not elementary. Yeah. So that, but yes, you are right. It depends. Okay. So these are theorems which gives you not everything, but a flavor about the decomposition of these special subvarieties into dense representation and faithful discrete, and there are something in between that I don't want to comment too much. I just comment that non-elementary representation are open also. This is clear by this definition because the fact if you have an action of a group on a space which does not preserve a probability measure, then a little perturbation of this action will not preserve also a probability measure. So, in fact, I am always thinking that the representations are non-elementary. Okay, so.
So you said a set of what do you have to remove for it to be open?
What's it? What's it? So you speak about?
You said, can you repeat what you just said?
So I said that the set of non-elementary representations, okay, is open. Okay. So now I would like to speak about algebraic instability versus structural stability. So I recall that in the talk of Ilyashenko explained that a lot of groups without, which are non-discrete, subgroups of PSL2C, for instance, are not at all structurally stable. They are rigid in a lots of different sense that he explained to us. I will just recall one of the theorem that can be proved, which is a really strong form of rigidity. That is, if you take two representations from the group G in PSL2C are dense, then any measurable conjugacy is, in fact, a Möbius, an element so a Möbius map, sorry, yes, it is a Möbius map.
Conjugacy of the action of P1,
Yes, so measurable, I will say. It's, in fact, a Möbius map, which can, I say Möbius map because eventually this map is not holomorphic, it reverses the orientation. It could reverse the orientation. Namely, if you take a representation and it's conjugate by the conjugacy, the complex conjugacy, then, of course, so measurable conjugacy, so it is stronger than the result that Ilyashenko was speaking about because it is just a measurable conjugacy with, but here we have a dense image, so we have a strong hypothesis. I will. I do that now. So, a conjugacy is a map phi from P1 to P1. So it is a conjugacy between ρ0 and ρ1, such that So we have the following relations for every G in the group, in our group G. And the conjugacy is, as I said, measurable if this map is measurable, continuous or topological if the map is topological, and so on. So in fact, from the point of view of measurable conjugacy, all the dense representations are different, or they are equivalent in a really strong way, that is, that are conjugated by a Möbius map.
Do you want this to be an equality or an equality almost everywhere?
So let's say that it is an equality for every point here, but it is true, in fact, almost. Okay, if it is a measurable conjugacy, it is sufficient to have a map which is defined, a conjugacy which is defined almost everywhere, and that these relations are defined almost everywhere to have the conclusion of the theorem, of the rigidity theorem. Okay?
So are your conjugacies invertible by hypothesis?
Sorry?
Are the conjugacies invertible by hypothesis?
Yes, this is a bijection. It is a bijection, sorry, yes. Is a bijection. Right. So, I will not speak a lot about dynamics, so I will just say that because we will need to have that in mind, that dense representations are really rigid in a dynamical sense. And now let us introduce the notion of algebraic stability. So for that, okay. Let's say, okay, we try. So a representation. So the idea is that a representation is algebraically stable. If you perturb this representation, then if for some element of G, rho of G was different from the identity, then this will be verified in a neighborhood of that representation, but for all G. Namely, the algebraic structure of the image of G does not change in the neighborhood of the representation. So namely, we don't pass in a... The kernel is fixed. Yes, this is exactly. Yes. So in other words, you don't pass in a spatial subvariety of dimension less than the spatial subvariety where we were. Yes, I will say that in the way Etienne said. So if there exists a neighborhood of rho in which neighborhood V such that the kernel of rho prime is equal to the kernel of rho for every rho prime in V. Okay. Now I will state a theorem that I proved by Sullivan. And this theorem will tell you one of the first statements that I announced in the beginning, namely that the union of all these spatial subvarieties is dense in the exterior of the set of structurally stable representations. So let me state this theorem. how I have to state it. So we start with a non-elementary representation of the same group G. So this theorem is going to say that algebraic stability is the same as structural stability. Okay? Structural stability means that there exists a neighborhood of the representation such that every representation in that neighborhood are topologically conjugated to the representation you started with. Okay? And it is clear that structural stability implies algebraic stability because the representation up to homeomorphisms are the same. So the image of the group, you can just think of the image of the group as being as a subgroup of homeomorphism of the sphere. And this subgroup does not change up to conjugacy. So the algebraic structure is the same. What is not clear at all is that the converse is true. Namely, if you have algebraic stability, then in fact you are structurally stable. So let's say like this. And in 3 minutes, I will try to explain you the proof. Of course, it's going to be a sketch. So the proof is based on the notion of holomorphic motion of a set of points in P1.
Sorry, the structurally stable is the same as rigid?
No, it's completely, no, it can be, I mean, rigid is structurally stable, but in a poor sense, in the sense that you cannot deform the representation. Okay? So it's...
What's the definition of structurally stable?
Structurally stable means that if you perturb, so you have a representation, if you perturb that representation, you get a representation which is topologically conjugated to the first one, but not necessarily, yes. So what is a holomorphic motion? You have of a set, so take the Riemann sphere P1 and take a set E of points in P1. So a holomorphic motion is a family of sets, let's say EZ, where Z is a complex number in the unit disk, and which are obtained are as a, which are exact in bijection with the set E, and such that the bijection corresponding to the point Z moves holomorphically. So namely, you have a family of points which depends on a complex parameter, and this family of points moves holomorphically in the Riemann sphere, and they never collapse. So two points never collapse for Z in the disk. So this is the definition of a holomorphic motion. And there is a remarkable and simple result which is called the lambda lemma, which is due to Magnier-Sade-Sullivan. So here, in the holomorphic motion, we don't have any hypothesis on the set F. It can be any set, okay, even non-measurable set, for instance, or any set. But if you have a holomorphic motion, the remarkable fact is that, in fact, the motion is continuous. Indeed, if you have 2 points which are close to each other at Z is equal to 0, they will stay close to each other, let's say, on a half disk during all the holomorphic motion on the half disk. And so you can extend the holomorphic motion to the closure of E. Okay? And so I just give a hint, and I finish here, to prove if you suppose, so suppose that you have a representation which is algebraically stable. We want to prove that in fact it is structurally stable. Then you can look in the image of the representation at all the transformations which are called loxodromic. Namely, these are transformations conjugated to that map with lambda in modulus different from 0 and 1, and which are 2 points, 2 fixed points on the Riemann sphere. One is repelling, the other is attracting. And it is quite easy to prove that if you have algebraic stability, then if at some parameter you have a loxodromic transformation, then it will stay loxodromic on all the open set of algebraic stability. And the fixed points of this loxodromic transformation defines a holomorphic motion, okay, because they cannot collapse. They are, this is also due to the algebraic stability. It is not so difficult to prove that. And these holomorphic motions gives you the topological conjugacy. So I am really, I go very fast here, but I have to stop. So I will stop here.